Hi everyone, welcome back. This is the second video for your Exam 2 material, so if you haven't watched the first one, go ahead and do that. What we're going to do today is just finish up the Chapter 16 material. Fun fact, this is my third time making this video because every time I do it, I forget to turn the microphone on, but the microphone's on this time, so we're ready to go. So we're just going to jump right in. So we're going to do a little bit of a review because these mechanisms or these reactions could come up on your exam again. They are fair game. You know, everything is cumulative. So let's just take the time right now to go over some old stuff that you might have forgotten. So oxidation of alcohols. So that was chapter 10 last semester, and we are going to talk about how we can go from an alcohol to an aldehyde to a carboxylic acid and all that interchanging. So if I have a primary alcohol, recall that I could selectively choose a reagent if I wanted to produce a specific functional group. That is, if I wanted to go from a primary alcohol to an aldehyde, I would use a weak oxidizing agent. And if I wanted to go from a primary alcohol to a carboxylic acid, I would use a strong oxidizing agent. So these are just listed for you before. The weak oxidizing agent, the only one that we know is PCC, so that brings a primary alcohol to an aldehyde. And if I wanted to go from the alcohol directly to the carboxylic acid, I would use a strong oxidizing agents such as Jones's or any of the dichromates that we see up here. New chapter 16 material, which really isn't new, but like they re-talk about it now in this chapter. If you wanted to go from an aldehyde, let's say, to a carboxylic acid, you would just use one of those strong oxidizing agents as well, Jones's or any of the dichromates to get there. All right, so the schematic of oxidation is adding in those carbon-oxygen bonds, I think by removing a hydrogen at the same time. So it goes from alcohol to aldehyde to carboxylic acid. So you see from left to right, it gets more and more complex with oxygen. All right, so let's just talk about secondaries and tertiaries for a second. Secondary, it didn't matter what type of oxidizing agent we used, regardless of it being strong or weak, we would still get a ketone because we were limited into the amount of carbon-oxygen bonds at that position. So if we had this alcohol, you see that the only thing that we can do is remove a hydrogen that is characteristic of oxidation, and then add in another carbon-oxygen double bond, but we couldn't add a third. There's no way to add a carboxylic acid here because we would exceed the octet at that carbon, so we would only be restricted to a ketone product. And in tertiary alcohols, the problem is that we have no room at all to add carbon-oxygen bonds, so there's no oxidation at all possible. So I'm going to show you what the theoretical product would look like if you guys were doing this at home. Adding in a carboxylic acid to this position in addition to the methyl group would mean there's 2, 4, 6, 8, 10, 12 electrons out of carbon. That is just so not happening. So that's why tertiary alcohols do not get oxidized. So that is an old review of all of our oxidations of alcohols. So now let's just jump into reductions. So that is Orgo 2 now, so we're learning how to go backwards. So we went from alcohol to aldehyde to carboxylic acid. That's left to right, so that is oxidation. If I wanted to do reduction, that's right to left. So that's carboxylic acid reduced to an aldehyde, reduced to an alcohol. And we have two different reducing agents that are used for these reactions, and those are the metal hydrides. So let's just talk about the difference in reactivity of these reagents, and then the schematic will make sense in a bit. So if I were to go over here, we have two different metal hydrides. We have sodium borohydride and lithium aluminum hydride. So if we wanted to talk about reactivity, the best trend to use, since they're in the same column, would be to talk about size. So as I go down the periodic table, I'm adding more and more shells. So size is increasing. Recall that when we form bonds with bulky atoms, those bonds tend to be longer because of the repulsions between the electron clouds of adjacent atoms. So a longer bond is a weaker bond, and that means it's more reactive. So let's just draw out the Lewis structures for sodium borohydride and lithium borohydride and rationalize, the reactivities of those. So sodium borohydride has a Lewis structure that looks like this. Negatively charged there, so that's why we have an associated sodium spectator ion. And then lithium aluminum hydride has a center aluminum with 4 hydrogens attached to it. Again, that's also a negative charge, and we have an associated lithium, hanging out to counteract that charge. We just said that aluminum is a lot larger, so I'm going to just draw a big circle to indicate size. Aluminum is a lot larger, so the hydrogen is a lot more reactive in the sense that it can be removed a lot more easier than the sodium borohydrides could be, because those bonds are more compact. So that makes sense that we would say that the lithium aluminum hydride reagent is more reactive, and then this one is less reactive. Okay, so that's going to make sense now when we look at the schematic. So obviously the carboxylic acid is the most it was the most oxidized version of an alcohol. So if I wanted to reduce it all the way back to the alcohol, I would need the strongest thing possible, and that's the lithium aluminum hydride. If I wanted to convert an aldehyde back to the alcohol, I would use just like the weak oxidizing agent. You could use LiH as well, but the weak one is sufficient enough to take that aldehyde to the alcohol. Sometimes, just if you want to see it on the exam, LiH is abbreviated, lithium aluminum hydride is abbreviated as LiH, so that's the same thing. Alright, so let's do some examples of those. Let's jump right in. So, something to note about these reductions. So, it's going to make sense in about 5 minutes when we're comparing all the different types of reactions, but the metal hydride reductions are specific to carbonyls only. Carbonyls only. So we see this molecule, we see an alkene, we know we're not touching that because these are metal hydride reductions. So the only thing we're going to touch in the first one, since it's a weak reducing agent, are the aldehydes and the ketones. We are not going to touch the carboxylic acid, and we're not touching the alkene. So it's a 5-carbon chain, 1, 2, 3, 4, 5, and we're going to have an alcohol, primary alcohol here, an alcohol here, and we're going to have, an alcohol here. 3, 4, 5. Yep, and don't forget that it's racemic at that position, so you would expect a wedge and dash configuration. Oh, I'm sorry. I don't know why I did that. You're not touching the carboxylic acid, like I said. Alright, so keep the carboxylic acid and the alkene, but you're only touching the aldehydes and ketones. Alright, so let's just look at LiH. For this one, so LiH is strong enough to do the carboxylic acid in addition to aldehydes and ketones, so we're going to take all 3 of those, but still not touch the alkene. So we have that 5-carbon chain, 1, 2, 3, 4, 5. We have that primary alcohol, we have the secondary alcohol that does have stereochem there, and we are now going to have that primary alcohol where the carboxylic acid used to be, and that is our final product. Don't forget wedges and dashes. So real quick, let me just show you the mechanism for how these hydrides, metal hydrides react. So if I were to just take a generic, aldehyde, and I were going to react with sodium borohydride, because I can use that weak reducing agent, what happens is that the hydrogen with its associated electrons are going to attack into the carbonyl and push up that oxygen pair, the pi electrons that are connected there, and then we are going to get, this tetrahedral intermediate with that hydrogen. So the hydrogen we just added over here is the hydrogen from here. All right, and then the final step is that water step. So you see step 1 is the sodium borohydride, step 2 would be water. So if I just had a molecule of water hanging out in solution, we would just expect that the mechanistic errors would be a lone pair grabbing that and pushing it on. So we now have formed a primary alcohol. So, oh, that's 2 carbons. We would form a primary alcohol, so CH3OH to be specific. All right, and that is pretty much it. So let's just move on to, the other reductions that we have over here. So catalytic reduction. So H2 and platinum, palladium, nickel is something we have seen before, but not in the context of carbonyl functional groups. So what H2 and platinum, palladium, nickel do is it's the strongest reducing agent ever. So if you remember that, it's the strongest reducing agent ever. It's going to reduce every single unsaturation point in here. So that's going to be the aldehydes, the ketones, the alkenes, and the carboxylic acid. So you would expect a product that looks like this. 1, 2, 3, 4, 5. You have that primary alcohol reduction. You have this tertiary, secondary is rather alcohol reduction, and remember it's chiral at that position. The alkene goes away to an alkane, and we have this primary alcohol over here. So that's the product of that. H2 and rhodium, that's a new metal that I haven't seen before. Rhodium basically is specific to only alkene reductions. So we're not going to touch the carbonyl containing functional groups here, so we can just draw everything as is and just draw it without the alkene. Alright, so let's just summarize all the different reductions we know. So H2 platinum palladium nickel is the strongest reducing agent, reduces every single unsaturation point in a molecule. Any of the metal hydrides are only specific to carbonyls, and more specifically, the sodium borohydride is only for aldehydes and ketones, but the lithium aluminum hydride can reduce any of those carbonyl groups, including carboxylic acids. H2 and rhodium is only specific to alkenes, so the alkene will be reduced, but none of the carbonyls will be reduced. So just remember that. All right. So reductive amination, it's not everyone's favorite. Surprisingly, it's really not that hard, but people just don't get it right on the exam. So the first step, even though they're together, coupled in reaction, I'm just going to draw them as 2 separate steps so you guys understand the logic that I'm using. So we use this NH2OH nucleophile. So it's a nitrogen-based nucleophile, And more specifically, it's going to be classified as a primary like. So by like, I mean it's not just a nitrogen-based nucleophile, there is an oxygen in there, so it's going to react as if it was a primary nitrogen-based nucleophile. So we're expecting an imine product. So the product of step 1 would be, this cyclohexane with an imine functional group, and we have, the OH over here. Okay, so that is the imine product of step 1, and sodium cyanoborohydride looks like sodium borohydride, as before, but we just replaced one of those hydrogens with a cyanide ion, and what's going to happen is this is going to reduce the unsaturation point, which is the alkene, and turn it into a amine. So it's going to look like this. And we don't cover the mechanism, so don't worry about that. Okay, so that is your final product. So it basically is reductive amination. It's reducing all the way to the amine. Okay, nothing too complicated there. Clemenson and Wolff-Kishner, so the final reductions in chapter 16. So let's just talk about these two. So Clemenson is the first one with zinc and mercury, and then Wolff-Kishner is the last one with hydrazine and potassium hydroxide. So the only they literally are the same thing. The only difference is that this is under acidic conditions, this is under basic conditions. So just be wary of any sort of side reactions. So for instance, if I were doing a Wolff-Kishner reaction with a carboxylic acid, we're not going to probably reduce that carboxylic acid carbonyl component because we have the acid-base reaction with that carboxylic acid. So, what I just said in a picture would be something like, if I had a carboxylic acid and I was putting it under, NH2, which is hydrazine, NH2, KOH and delta, I'd probably have a KOH and H, reaction where I would just form an alkoxide anion instead of, my actual product, which is the alkane. All right? That's just something to, be cognizant of. Anyway, so the purpose of this reagent is to reduce these with these carbonyl groups and replace it with a methylene. So methylene is just CH2. So if I were to draw that product, it's just the same thing. We're not touching any of that. But it's just going to be at this position, over here and over here. Now they are reduced to just these methyl groups. Likewise over here, this methyl group, this carbonyl and this carbonyl are going to turn into just a plain cyclohexane molecule. Done. That it. All right. So now keto to enol tautomerization. So we talked about this before in Orgo 1. So let me just draw this again. So this is the keto form. This is the enol form. Okay, and we said in Orgo 1 that the keto form is more stable than the enol because the keto has a strong carbon-oxygen double bond versus the relatively weak carbon-carbon double bond, so the keto was preferred at equilibrium. So now we're actually going to see why in the mechanism that sometimes the enol is actually preferred. Alright, so this mechanism can happen under either acidic or basic conditions. So if I were to do this under acidic conditions, I would draw the ketone first. So actually, let me just start with an aldehyde. And if I were to place it under sulfuric acid conditions, like H2SO4, I can draw the Lewis structure, which looks like this. Okay? And the role of an acid, like we always said, was to protonate that carbonyl to make it more electrophilic. So these would be the first sets of mechanistic arrows. So we would see something like this. Oops, I'm sorry. We would see something like this. All right, so now what can happen is that at this alpha position, so one carbon removed is always called the alpha position. Let me change colors. This is the alpha position. I can draw in the relative, there's 3 hydrogens here, okay? So what happens is that the conjugate base of sulfuric acid is going to remove one of those protons from the alpha position, donate that electron density in, and push those pi electrons up on the carbonyl. So our final structure is going to be something that looks like this. Okay, and now we formed the enol. So that's the mechanism. If you wanted to go backwards, just do the same steps in reverse. So it's not too difficult. All right, so let me just show you the basic conditions. So that's acidic conditions. And now let's do the basic conditions. So if I draw that same generic, aldehyde, and I were to react it with sodium hydroxide. So again, the role of the base is not to make the electrophile more electrophilic, but rather to just foster the removal of that alpha hydrogen on its own. So what we're going to do is we're going to take that hydrogen off, we're going to donate that electron density in, push those pi electrons up, and then we're going to get a structure that looks like this. So we're almost there. We just have this alkoxide anion, and the last step is we just made water, so we're just going to take a hydrogen off of the water. It's under basic conditions to regenerate that hydroxide catalyst, and then we just formed our enol. Okay, so those are the two mechanisms. They really aren't that bad, and again, if you wanted to go from enol to keto, it's the same thing in reverse. All right, so now let's just talk about why sometimes maybe an enol would be preferred at equilibrium. So if I just drew like two generic, ketones, and I would just say that arbitrarily one of them turns into an enol, doesn't matter, I'm just picking one of them, I want to show you that there are some extra stabilizing features that you may not have been aware of before that cause this whole molecule to be in an enol state. All right, so it's twofold actually. There's two reasons. So the first one would be something called hydrogen bonding, which I'm sure you guys are all familiar with. So the hydrogen bond would be between the enol and the ketone of the beta position. So let me just say that this is alpha, this is beta. So at that beta position, we are sufficiently far enough away to have this interaction where the hydrogen of the enol interacts with the oxygen of the ketone, and we have a stabilizing feature, which is hydrogen bonding. The second stabilizing feature would be something called conjugation. And we're going to have a whole chapter on conjugation later on in the semester, but conjugation basically just refers to a pattern of sigma bonds with pi bonds with sigma bond with pi bond all in a row. It has to be alternating sigma pi, sigma pi, sigma pi. All right, so if I were to look over here, I see I have a sigma bond, then I have a pi bond, then I have a sigma bond, and then I have a pi bond. So that alternating pattern is a stabilizing feature. We'll talk more why it's stabilizing later on in the semester, but we see that this is going to be preferred at an enol is going to be preferred at equilibrium because we have hydrogen bonding in addition to conjugation. So knowing that knowledge, let's just do an example problem on the exam. So let's just convert these to their enol forms first. So I can just pick in molecules with more than one carbonyl functional group. You can just arbitrarily pick one. Doesn't matter. And then let's just do this one, so OH, and then let's just do this one over here. So this molecule is going to be like this. Okay, so let's just think about the features. So let's just make a chart here. So hydrogen bonding and conjugation. So these are my charts. All right, and let's just verify if these exist. So if we look at our first molecule, we most definitely do have hydrogen bonding because this is the alpha position, this is the beta position. It's sufficiently far enough away to do that interaction, so we do have hydrogen bonding. In terms of conjugation, do we have that? Well, we have a pi bond next to a single bond next to another pi bond. So we most definitely do have conjugation, so we have both stabilizing features. Let's move on to the next one. Do we have hydrogen bonding? Well, here's the alpha position, here's the beta position, and here's the gamma position. Ooh, it is not in the beta position, so we do not have, and we also don't even have a ketone or any carbonyl functional group to do hydrogen bonding with, so we most definitely do not have hydrogen bonding. In terms of conjugation, let's see. So we have a pi bond next to a sigma bond next to another sigma bond. Oh, that's not my trend, so no, we do not have conjugation. Let's look at this final structure. Here, we don't have hydrogen bonding because, we don't have any ketone or carbonyl groups in the beta position, so no hydrogen bonding, but we do have conjugation with the benzene ring, actually extensive conjugation. So pi bond, oops, that's not the highlighter. We have a pi bond followed by a single bond, followed by a pi bond, single bond, all in the ring, so we do have conjugation. So if I were to, rank these now based on the knowledge of my stabilizing features, oops, I would say that this would be number 3, this would be number 2, and that would be number 1. All right? So now let's just do the last two topics here. We have Rasterization at the alpha position. So this is a special topic. It's not really, I guess, it's not really like a reaction you memorize. It's just like a side thing that happens, as a result of keto to enol tautomerization. So the first step in this reaction is just to do keto to enol tautomerization because we are under acidic conditions. So the first thing that I would do in the mechanism would be to draw out sulfuric acid. So actually in this case, I'll just do this. So OH and then OH. And what happens is the role of the acid is always to make the electrophile more electrophilic. So we're going to grab a proton and we are going to form, a protonated carbonyl group. So it looks like this. And now it's sufficiently electrophilic. So now I'm just going to draw in the hydrogen on a dash to kind of show you why that is in the mechanism in a second. So I'm going to draw the conjugate base of sulfuric acid because we just formed that in the last step. So the role of the conjugate base now is to remove the hydrogen from the alpha position, donate that electron density into the ring, and then push those pi electrons up. So basically now we just formed something like this. And is that an enol? Yes, it is. So we just did keto to enol tautomerization. That's easy. We know how to do that at this point. But I do want to make a comment about the stereochemistry at this position. So before, the stereochemistry was on a wedge configuration, and now the stereochemistry is in plane. So if I were to go back to the keto form, so if I were to just write here, keto tautomerization, so let's just draw that structure. So the keto is now like this. So we would have the OCH3 back here on a plane, but now we just formed a new chiral center. So we would expect both wedges and dash configuration. So the products of this reaction are actually OCH3, and then on a wedge, and then OCH3 on a dash. Okay, so that's what we talk about Rasterization at the alpha position. When we have a substituent at an alpha position and we can subject it to like an acid or base catalyst, keto to enol tautomerization does take place, and a consequence of that tautomerization is Rasterization of a substituent at the alpha position. All right. That's all that this special topic is. So if you see this on the exam, just, there's no thinking, it's just rating both enantiomers of that starting material. All right, and finally we have alpha halogenation. So you are not going to be tested on base catalyzed, so that's good news, and I'll talk about why in a minute, but you will be tested on acidic conditions, so let's just talk about that. So the first thing again is to make keto to the enol tautomerization, so it's going to be something like this. Okay, and I'm just going to draw in a hydrogen. So this is acetic acid that we're reacting with. So again, the role of the acid is to make the electrophile more electrophilic. So we're going to grab a proton, donate it there, and we are going to form, this structure. So now we have a protonated carbonyl. All right, and now what we can do is tautomerize. So we're going to take that acetate anion, and it's going to deprotonate that hydrogen on the alpha position, donate that electron density in, push those pi electrons up, and then we finally form, this enol. Okay, so we now have that enol. So the driving force of the halogenation at the alpha position is actually resonating those pi electrons down on the oxygen. So if we resonate those down, we have to kick these carbon pi electrons out and grab a bromine, okay? So the product of that is going to be something that looks like this. And then that final step is just taking that bromine anion and, grabbing that final hydrogen off of the carbonyl to fix it, okay? So now we are back to that structure. Okay, so that is halogenation. So what's wrong with basic conditions is this. So at this alpha position, there are two more hydrogens. So let me just draw the starting material again over here. So if I drew, the benzene ring, and I drew this, and I have three hydrogens here. All right, so both of these sets of molecules have acidic hydrogens because of their proximity to electronegative groups, but more specifically, these hydrogens are close to not one, but two electronegative groups. When we said that when when we said molecules are very electronegative, they are more acidic. So what happens is under basic conditions, we would continuously remove these hydrogens and replace them with bromines because, the acid-base reaction is going to constantly remove these and constantly remove these. So we have something called polyhalogenation happening. So that's why we can't test you on this, because who's to say that you're not going to have two instead of three, or just one by chance? There's no way to predict one specific product, so that's why we can't test you on basic conditions. But acidic conditions, you only get that one halogen at the alpha position. All right, I hope that helps.